Hi everyone, I'm Alexandra Cortez, and we're at the Anthropomorphic Robotic Arm. I just want to go over the objectives of our team. Right now, I'm sure most of you have remembered that our main focus was building an anthropomorphic robotic arm, but a few changes have been made. Instead of focusing on the entire structure of a human arm, we're now just purely focusing on the actuators of the robotic arm, and, or as you know, artificial muscles. And our objective is to create dielectric elastomers for linear actuators. And our two major goals right now, which we've semi-accomplished during this internship, is contain the materials needed to make the dielectric elastomer and to run experiments to better understand formulas applied to them, according to research.
So there's two entities when it comes to this project. We have the power supply and we have the elastomers. Power supply, just an average power supply, and it just needs to generate 3 to 7 kilovolts, 3,000 volts, 7,000 volts in order for the actuators to work. And the actuator is made up of what we call an elastomer. It's a type of rubber that acts as a dielectric and a capacitor. So when we have the two on each side of the rubber, we have 2 plates. They're made of carbon grease, and when we pass the electricity through it, it deforms the rubber, and it stretches and it contracts, making a mechanical motion, which is what we're looking for. So after a couple of tests and stuff, we're going to be looking for optimal results that can be used practically for the arm.
The calculations for this, we have the maximum stress. The maximum stress is important to calculate how much stress the elastomer can handle in a given experiment. We have some equations called maximum stress. So we have the first one equation. The maximum stress is calculated as given in the equation 1. For this equation was derived from the stress equation that you can see there, that it has a 1/2 instead. For this thing, we have three different types of stress, but in our case we have, and we choose the stress called uniaxial stress, because we can see in this case when we apply voltage, we can see in both sides that we're going to apply. So in this case we used that equation because we're going to do the arm, so it's going to apply top in the bottom.
So in the Maxwell stress equation, we need to calculate the permittive of the material. And for that, we're going to use the equation 3. That's dielectric constant is permittive of material divided by the permittive of vacuum. But the problem is we need to know also the dielectric constant. So we're going to use the equation 4 to calculate the dielectric constant. So is capacitor is equal to the dielectric constant multiplied by the permittive of vacuum and multiplied by the area divided by the distance.
So the first thing that we did was we ran we ran an experiment. So what we did was we built a capacitor using aluminum sheets as plates. And basically our intention with that was to place paper in between the plates to then find the dielectric constant of the paper. So a multimeter was used to measure the capacitance of our capacitor when we placed our paper, which is our dielectric in between the plates. And then once we got that capacitance, we used the equation 4, which Marcos just explained, to then find our dielectric constant of the paper. And so the purpose of running this experiment was to then understand how we could find the relative permittivity or the dielectric constant of our dielectric elastomer material when we get it. And so getting a value, an experimental value as close as possible to the actual value of paper would then give us a way to move forward when we get our material.
Okay, so this graph represents the electric breakdown, and it shows the equilibrium between voltage and strain. And when these two things are at a reaching point, this is when the electrical breakdown occurs. So once the breakdown occurs, the dielectric elastomer will no longer expand and contract, and that is when the voltage is applied. So to prevent the breakdown, E must always remain less than the breakdown strength.
So the one thing we have to keep in mind when we're actually building the dielectric elastomer is, like she said, the electrical breakdown, or also known as the voltage breakdown. At some point, the voltage gets too high, so the temperature rises as the voltage increases, making the material softer. And when it's soft, it gets thin, and once it's too thin, it'll break. So that's the electrical breakdown.
How much more you have? Almost done?
Yep.
That's it?
Yes.
Yeah.
All right.
Thank you.